Some of the most biologically important functional groups that contain the carbonyl bond are the carboxylic acids and their derivatives, and we'll tackle those in this video. Our learning goals will include the structural factors that enhance acidity, differentiating between various carbonyl functional groups, and the hydrolysis reaction which connects the carboxylic acid derivatives with their parent carboxylic acid. Let's begin by considering the factors that influence acidity. Recall that acids are basically substances that can donate H+ ions. H+ is sometimes called a proton because when you take the electron away from the hydrogen atom, all that's left is a proton. Now, not every hydrogen in a hydrocarbon molecule is going to be susceptible for donation as an H+ ion. So we want to look at what this acidity particularly depends upon. Obviously, the electronegativity of the atom to which hydrogen is attached is going to make a difference, because if it's more electronegative, it can withdraw electrons from the hydrogen, making it more likely that it can be lost as a proton. We'll also care about the strength of the bonds that hydrogen makes with whatever it's attached to, and the electron withdrawing capacity of the rest of the molecule. If the other parts of the molecule draw electrons away from the part where the hydrogen is, that will also make it more acidic. Finally, we'll be interested in the stability of the anion that remains after the H+ is removed. If it's more stable, it turns out it'll be easier for us to get that hydrogen off and therefore make it more acidic. The best candidates in this case are when hydrogen is attached to oxygen, sulfur, or nitrogen. Almost all acids, organic or inorganic, have hydrogen attached to one of these, also to the halogens, which are very electronegative. Now, the relative electronegativity can affect the charge separation of the direct bond that hydrogen is involved in. And it turns out that carboxylic acids are really good at removing electron density from these hydrogen atoms. In other words, that carbonyl bond is such a polar bond and such a withdrawing effect that it pulls electrons away from the OH, and the oxygen already is electronegative, so the hydrogen is left out there very susceptible to loss as an H+ ion. So it in fact is the most acidic hydrogen in a compound that contains this particular functional group. Now, here are 3 carbonyl containing compounds, all with 3 carbons and a carbonyl bond. Propanal, which is an aldehyde, acetone, which is a ketone, and propionic acid, which is the carboxylic acid. And I think you can see here that the H at the far right end of the propionic acid is very positively charged according to the MEP surface, and it is by far the most acidic proton, most acidic hydrogen on any of these compounds. The other 2, propanal and acetone, do not really behave as acids at all. So another thing that enhances the acidity of carboxylic acids is the resonance that's formed in the ion that's left behind, which is called the carboxylate ion. All right, so here's what a carboxylic acid looks like when H+ has been removed, and you'll see that H+ removes without taking its electron with it, so it leaves behind a negative charge on that oxygen. But that oxygen now can share that negative charge with the other oxygen through a resonance structure. So consider the fact that we have these 2 things that can now move electrons in this way to form a completely equivalent resonance structure to the one that was created by the loss of the hydrogen. The fact that these carboxylate ions can do this means that they're going to be a lot more stable once they've lost the hydrogen, and that charge delocalization causes the hydrogen that's attached to the carboxylic acid group to be more acidic. So this is really the key to what makes carboxylic acids stronger acids than basically any other hydrocarbons that we'll encounter. An inductive effect is one that increases acidity by having strong electron withdrawing groups near the carboxylic acid group. So a lot of times this includes halogens, but it also can include things like the cyanide group, can include nitro group, or methoxy group. This particular thing called an inductive effect, and let's take a look at how that might affect things. So here's acetic acid, and then we might add a chlorine to the methyl group on acetic acid, 2 chlorines, or 3 chlorines. Okay, so this creates a series where we've increasingly added the electron withdrawing effect of the chlorine to these acetic acids. So what would be the relative acidity in this case? Well, if acetic acid is 1, chloroacetic acid is 63 times more acidic. Dichloroacetic acid is 2,500 times more acidic, and trichloroacetic acid is 6,300 times more acidic. So you can see directly that the addition of these electron withdrawing groups, this inductive effect, has greatly increased the acidity of what originally was acetic acid. All right, let's take a look at the carboxylic acid derivatives. These are basically other functional groups that have a relationship to the parent carboxylic acid, but they are functionally different. So for example, an ester has, instead of having a hydrogen attached at the end of the carboxylate group, it has an alkyl group. An amide, instead of having the OH, has an NH2. The acyl chloride has a chlorine. And the acid anhydride is basically a fusion of two carboxylic acids in a way, minus a water that was subtracted in that. When we look at their MEP surfaces, we can see that they are distinctive from the carboxylic acid group in that they don't have any obviously acidic protons attached there. All right, so how are these related to the carboxylic acid? What makes them carboxylic acid derivatives? Well, it's related to a reaction called a hydrolysis reaction. Now, let me define that. Hydrolysis comes from the Greek words hydro and lysis, hydro standing for water, and lysis to break. So in essence, a hydrolysis reaction is one in which water inserts into a bond between the carbonyl bond and the derivative group, and in doing so, it breaks that bond. So we're going to create two new molecules from this. So let's see figuratively what this does. So here is one of the carboxylic acid derivatives, and I've designed its derivative group to be called X, so we can cover all of the different functional groups. Okay, so this is an acid derivative. When water comes up, essentially what happens is there's a little bond rearrangement that occurs where the carboxylic acid derivative, that derivative group X, forms a bond to the hydrogen, and the OH forms a bond to the carbonyl group. The net result is going to be the parent carboxylic acid, as well as the derivative for the derivative group bonded to hydrogen. So the derivative groups in this case mean OR for ester, or it could be NH2 for the amide, chlorine for the acyl chloride, or this acid anhydride group. All right, so when H attaches to each of these, when it attaches to that ester derivative group, it would form an alcohol. When it attaches to the amide, if it's a primary amide, as we've shown here, it would just make ammonia. If it attaches an acyl chloride, it forms HCl, hydrochloric acid. And if it attaches to the acid anhydride, it's actually going to form another carboxylic acid from that. Now, I should note that the actual hydrolysis process is a lot more complicated than what I've drawn here. I've tried to draw it this way for clarity so that you can see the effect of the water adding to this. I should also mention that only the acyl chloride really does this in a very facile fashion, that the amide is the acid anhydride is the next most effective one, then the amide, and then the ester. It's very difficult to hydrolyze esters, and oftentimes in biological systems it requires an enzyme to facilitate that.